Something is pulling at the edge of our solar system. You can feel it in the math. You can see it in the way the darkness is moving. Out there, 500 astronomical units from the Sun, far beyond Neptune, far beyond anything you learned about in school, dozens of distant rocky worlds are being twisted and herded by an invisible hand. Their orbits don't make sense. They shouldn't be where they are, tilted the way they're tilted, clustered the way they're clustered. The probability of this happening by random chance is 0.00006%, 1 in 14,000. And for the last 10 years, scientists have been telling us the same story. They say there's a hidden planet out there, a super-Earth, 5 to 10 times the mass of our world, silently circling the Sun on a vast elongated orbit that takes 20,000 years to complete. They call it Planet 9, and they promised us that any day now, we'd find it. They said all we needed to do was look in the right spot. Well, we've looked. We've scanned 80% of the southern sky. We've used the Subaru telescope in Hawaii. We've used the Zwicky Transient Facility. We've used the Dark Energy Survey. We've combed through 40-year-old infrared satellite data. And you know what we found? Nothing. Absolutely nothing. The sky where Planet 9 should be is empty. The orbit is silent. But here's what hasn't changed. The math. The gravity is still there. Something with the mass of 5 Earths is still pulling on the outer reaches of our solar system. If it's not a planet, then what is it? What kind of object has the mass of multiple Earths but emits no light, reflects no sunlight, and has remained invisible for a decade of intensive hunting? There's a theory that was quietly published in 2019 and mostly ignored. But in the last few months, as the searches keep coming up empty, this theory is becoming less fringe and more frightening. It suggests we haven't found Planet 9 because Planet 9 isn't a planet. It suggests that for the last 4 billion years we've been sharing our solar system with a primordial black hole, a grapefruit-sized puncture in space-time, invisible, silent, heavy, and the machine that can finally detect it just turned on. The Vera Rubin Observatory in Chile is now operational, and in the next 12 months we're going to find out if our solar system has been hiding a ghost from the beginning of time. I'm Mikhail, and if you thought we lived in a 9-planet solar system, or an 8-planet solar system, you might want to reconsider. Because the 9th sibling might not be a sibling at all. It might be something much, much stranger. Let me show you why planetary scientists are starting to lose sleep. The story begins not with modern telescopes, but with a man named Urbain Le Verrier in 1846. He was sitting at his desk in Paris with nothing but a pen, paper, and Newton's laws of gravity. He was studying Uranus, the 7th planet, and Uranus was misbehaving. It was speeding up when it should slow down. It was drifting off course. Its orbit didn't match the predictions. Now, most astronomers at the time thought maybe Newton's laws were wrong. Maybe gravity worked differently at the edge of the solar system, but Le Verrier didn't accept that. He knew gravity doesn't lie. If Uranus was being pulled, something had to be pulling it. So he did the math. He calculated where an unseen planet would need to be to cause the exact disturbances they were seeing. He wrote down coordinates, sent them to an astronomer in Berlin, and that night they pointed the telescope at the spot Le Verrier had calculated, and there it was, Neptune, a planet discovered not by seeing it first, but by feeling its gravity. It was the greatest triumph of celestial mechanics in history. We found a planet using nothing but math, and ever since that night, astronomers have been trying to do it again. Decades later, they noticed Neptune itself was acting strange. Something was tugging on it too. So they searched. And in 1930, Clyde Tombaugh discovered Pluto. They thought the mystery was solved. But Pluto turned out to be too small. Far too small to pull on Neptune. The discovery was a fluke, and for decades we thought we were done. We thought the map was complete. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. And out past Neptune, the debris field of the Kuiper Belt, a graveyard of icy rocks left over from the formation of the solar system. Cold, dead, stable, predictable. But in 2003 everything changed. Astronomers discovered Sedna. Sedna is a dwarf planet about the size of Pluto, but it orbits in the middle of nowhere. It never comes close to Neptune. It never interacts with the Kuiper Belt. Its closest approach to the Sun is 76 astronomical units. That's twice the distance of Neptune, and at its farthest point, Sedna swings out to nearly 1,000 astronomical units. It takes 11,000 years to complete one orbit. And here's the problem. Sedna shouldn't exist. You can't form a rock that size in a region that's empty. There's not enough material out there. The only way Sedna makes sense is if something dragged it there. A passing star, maybe. A rogue planet. Or something we haven't thought of yet. For a while, astronomers treated Sedna as a strange outlier. A cosmic accident. But then they found another one, and another. By 2014, a pattern started to emerge. Astronomers Scott Shepherd and Chadwick Trujillo looked at the handful of extreme trans-neptunian objects we'd discovered. These are the loneliest rocks in the solar system, and they noticed something disturbing. The rocks were clustered. Imagine you throw a handful of marbles across a room. They should scatter randomly in all directions, right? But these marbles were all bunched up on one side of the room. Their orbits were tilting the same way. The point where they come closest to the Sun, the perihelion, was aligned within a narrow range of angles. The odds of this happening by chance are almost zero. It's like shuffling a deck of cards and pulling 5 aces in a row. It doesn't happen. Unless the deck is stacked. In 2016, 2 scientists from Caltech, Konstantin Batygin and Mike Brown, took this data and ran simulations. They asked the computer what could cause this clustering, and the computer gave them an answer. It said there's a massive object in the outer solar system, a planet roughly 5 to 10 times the mass of Earth, orbiting on a highly elliptical path somewhere between 400 and 800 astronomical units from the Sun. They called it Planet 9, and it was a perfect solution. It explained Sedna. It explained the clustering. It even explained why the Sun's rotation axis is tilted 6 degrees relative to the plane of the planets. It solved problems astronomers didn't even know existed. Everyone got excited. Mike Brown, the man who killed Pluto by discovering Eris, said he was 80% confident we'd have an image of Planet 9 within 5 years. Major observatories started dedicating time to the search. Citizen scientists joined the hunt, blinking through millions of telescope images looking for a faint dot that moved between frames. They thought it would be easy. A super-Earth at 400 astronomical units should be faint, but visible. It should be glowing in the infrared just from its own internal heat. Even if it's cold and dark, it should reflect a tiny amount of sunlight. We've found dwarf planets farther away than that. We've imaged exoplanets orbiting other stars dozens of light years away. Surely we can find a planet in our own backyard. Well, it's been 10 years, and we've found nothing. The Zwicky Transient Facility has mapped the northern sky repeatedly. The Dark Energy Survey scanned the southern hemisphere. Pan-STARRS 1 has been running for over a decade. The WISE Infrared Space Telescope has looked at the entire sky multiple times, and the result is always the same. Empty space, no planet, no dot moving against the background stars, no infrared glow, nothing. But the clustering is still there. In fact, it's gotten stronger. Since 2016, we've found more distant objects, and they fit the pattern. The gravity is real. The perturbations are measurable. The math hasn't changed, so if Planet 9 is out there, and it has the mass of 5 Earths, why can't we see it? This is where things get strange. In September 2019, 2 physicists named Jakub Scholz and James Unwin published a paper that most of the scientific community ignored. They asked a simple question. What if Planet 9 is not a planet? What if it's a black hole? Now I know what you're thinking. Black holes are massive. They're the corpses of dead stars. The smallest stellar black hole is about 3 times the mass of the Sun. If we had something that heavy in our solar system, we wouldn't be here. It would have torn the planets apart a long time ago. But Scholz and Unwin weren't talking about stellar black holes. They were talking about primordial black holes. These are ancient ghosts. They weren't born from dying stars. They were born in the first fraction of a second after the Big Bang. In those earliest moments, the universe was a hot, chaotic soup of energy. There were density fluctuations, tiny wrinkles in space-time, and in some spots those wrinkles were so dense that they collapsed under their own gravity before the first atoms even formed. Before the first stars were born, these are primordial black holes, and the theory says they can be any mass. You could have a primordial black hole the size of a proton. You could have one the mass of a mountain. You could have one the mass of Earth, or 5 Earths. Scholz and Unwin calculated what a primordial black hole with the mass of 5 Earths would look like, and the answer is terrifying. It would be invisible. because the event horizon, the sphere of darkness from which no light can escape, would be about the size of a grapefruit, 10 centimeters across. Think about that. The entire gravitational mass of 5 Earths crushed into a ball you could hold in one hand. It's out there right now, orbiting the Sun, pulling on Sedna, herding the Kuiper Belt objects into their strange clustered orbits. And we can't see it, because you can't photograph a grapefruit at 400 astronomical units. It doesn't reflect light. It doesn't emit heat in a way our telescopes can detect. It is the perfect stealth object. But it still has mass. It still bends space-time. It still pulls on everything around it. And that explains everything. It explains why the gravity signatures match a 5 Earth mass object. It explains why we haven't found it despite a decade of searching. It explains the clustering, and it raises a deeply uncomfortable question. If a primordial black hole captured by our solar system billions of years ago is statistically possible, then how many other solar systems have one? How common are these invisible shepherds lurking in the outer darkness? And more importantly, is there evidence? Schultz and Unwin pointed to something called the OGLE data, the Optical Gravitational Lensing Experiment. This is a project that watches millions of stars looking for brief brightness changes. Sometimes a star suddenly gets brighter for a few hours because a massive object passed in front of it. The gravity of the object bends the starlight like a magnifying glass. This is called gravitational microlensing. We usually use this technique to detect rogue planets floating through the galaxy without a star. But the OGLE data has anomalies. There are 6 events that don't fit the profile of a rogue planet. They were too short, too sharp. The lensing signal looked exactly like what you'd expect from a very small but very dense object. Like a black hole the size of a grapefruit. A population of Earth-mass primordial black holes drifting through the Milky Way would create exactly this kind of data. If that population exists, and our Sun passed through a region dense with them 4 billion years ago, capturing one is not just possible, it's likely. Some astrophysicists estimate the capture probability is roughly the same as capturing a rogue planet. 50-50. So scientifically, it's just as plausible that Planet 9 is a black hole as it is that Planet 9 is a planet. And that realization is starting to shift the conversation, because if we're looking for the wrong thing, we'll never find it. We've been searching for reflected sunlight, for infrared glow, for a dot that moves, but a black hole doesn't shine. It doesn't move like a planet in our images because it's too small to resolve. We need to look for something else. We need to look for the destruction it causes. A black hole doesn't just sit silently in space, it interacts with its environment. The outer solar system isn't completely empty. There's dust, ice, gas, tiny fragments of rock. And if a primordial black hole is moving through that environment, it will feed. Not much. It's too small to swallow anything large. But as dust and ice fall toward the event horizon, they accelerate, they heat up, they collide with other particles, and for a brief moment, they emit light, flashes, flickering. Schultz and Unwin calculated that if Planet 9 is a black hole, it might produce faint transient flares, little sparks in the darkness. And there's another signature we can look for: occultation. There are billions of catalogued stars. If a black hole passes directly in front of one of them, it won't block the light like a planet would. It will lens the light. The star will suddenly brighten, then dim, in a very specific pattern. If we see that happening in the exact region where Planet 9 should be, that's not a coincidence. That's a detection. And the machine that can catch these events just came online. The Vera Rubin Observatory in Chile. This isn't just another telescope. This is a time machine, a survey engine. It has the largest digital camera ever built, 3.2 gigapixels, the size of a small car. It's going to photograph the entire southern sky every 3 nights. For 10 years. It's going to create a movie of the universe. Every asteroid, every supernova, every star that blinks, every object that moves. And it's sensitive enough to detect the faintest, most fleeting events. If Planet 9 is a planet, Vera Rubin will find it. The telescope is designed to see objects 100 times fainter than previous sky surveys. If there's a super-Earth out there reflecting even a trace amount of sunlight, Vera Rubin will catch it within the first year of operations, but if the first year passes and the sky's still empty, that's when the black hole hypothesis stops being the fringe theory and becomes the leading candidate. Because Vera Rubin is also the perfect tool to find a black hole. It's a transient hunter. It's designed to see things that change. If there's a flickering accretion disk around a tiny black hole 500 astronomical units away, Vera Rubin will see the flicker. If a star gets lensed by a grapefruit-sized singularity, Vera Rubin will catch it. The data is already streaming in. The survey officially began in 2026, and the first results are being analysed right now. Every night, 20 terabytes of data, millions of objects tracked, and somewhere in that data there might be a signal, a flicker, a lens, a ghost. The implications of this are staggering. If Planet 9 is a black hole, it means our solar system is not just a family of planets orbiting a star. It's a trap, a cage. We caught a monster from the dawn of time and kept it as a silent companion for 4 billion years. It means there's a laboratory for studying quantum gravity sitting in our own backyard. We could send a probe to it. We could study the event horizon up close. We could test Hawking radiation. We could answer fundamental questions about the nature of space-time without leaving our home system. This would be the greatest discovery in the history of astrophysics. Or it could mean something darker. Because a black hole is a chaotic object. If it's out there, interacting with the Oort cloud, the vast shell of icy comets surrounding the solar system, it could be flinging objects toward the inner planets. Some scientists have suggested that long-period comets, the ones that take thousands of years to orbit, might be getting perturbed by Planet 9. If Planet 9 is a black hole, and it's destabilizing the Oort cloud, we might see an increase in comet impacts over the next few centuries, and we wouldn't know until they're already on their way. But let's go back to the evidence. Because whether it's a planet or a black hole, the case for something being out there is stronger than ever. The clustering isn't the only anomaly. There's also the detached objects. These are worlds like Sedna that never come close to Neptune. They orbit entirely beyond the influence of the known planets. Sedna 2012 VP113, the Goblin, they're moving in lockstep, as if something is conducting them. Then there's the retrograde orbits. Most objects in the solar system orbit the Sun in the same direction the planets do, counterclockwise if you're looking down from above the North Pole. But there are a handful of objects out there that orbit backward, clockwise, retrograde. This shouldn't happen unless something kicked them into that orbit, a passing star maybe, or a massive object still out there. And there's the inclination problem. The plane of the solar system, the ecliptic, is defined by the orbits of the planets. Most objects stay close to this plane, but the extreme trans-neptunian objects are tilted, some by 30 degrees, some by more than 40. Gravitational simulations show that a 5 Earth mass object on an inclined orbit could lift these distant rocks out of the ecliptic over millions of years. The more data we gather, the tighter the case becomes. Mike Brown and Konstantin Batygin published an updated analysis in 2021. They ran thousands of simulations. They tested every alternative hypothesis, observational bias, random chance, a belt of small objects instead of one large planet. None of the alternatives fit as well as Planet 9. The statistical significance is now over 99%. Something is out there, but we still don't have a picture, and that silence is starting to feel intentional. Now, I'm not saying there's a cover-up. I'm saying there's a gap between what the data suggests and what the public narrative emphasizes. NASA talks about Planet 9 in press releases. It's not a secret. But the primordial black hole hypothesis, that's buried in academic journals. You won't see it on the evening news. Why? Because the implications are too strange. If we announce that our solar system might contain a black hole, the public reaction would be fear. People would panic. They'd ask if it's dangerous, if it could swallow the Earth. And the answer is no, it can't. A 5 Earth mass black hole has the same gravity as a 5 Earth mass planet. It's not going to suddenly eat Jupiter. Gravity doesn't work that way. But try explaining that to a public that thinks black holes are cosmic vacuum cleaners. So the scientists are being cautious. They're waiting for definitive proof. They're waiting for Vera Rubin to either find the planet or find the lens. And that proof is coming. In the next 12 months, we're going to know. Either Vera Rubin will photograph a new super-Earth in the outer solar system, or it will detect a microlensing event that matches the predicted orbit of a primordial black hole. Either way, the mystery ends. The 9th object in our solar system will finally have a face, or a shadow. So where do we stand right now? We know something with the mass of 5 to 10 Earths is orbiting the Sun somewhere between 400 and 800 astronomical units away. We know it's perturbing the orbits of distant objects in a way that can't be explained by random chance or observational bias. We know that a decade of searching for reflected sunlight has come up empty. We know that the capture probability of a primordial black hole is statistically comparable to the capture probability of a rogue planet. We know that the OGLE microlensing data includes anomalies consistent with the population of Earth-mass black holes in the galaxy. We know that the Vera Rubin Observatory is now operational and scanning the sky every 3 nights. And we know that within 12 months we should have an answer. But there's one more thing we need to talk about: the alternatives. Because not everyone believes in Planet 9. Some scientists argue that the clustering is an illusion, a result of observational bias. We search for distant objects in specific parts of the sky because that's where it's easiest to search. We avoid the galactic plane because it's too crowded with stars. We avoid the southern hemisphere because most big telescopes are in the north. So maybe we're just finding clustered objects because we're only looking in one direction. The OSOS survey, the Outer Solar System Origin survey, tried to account for this bias. They carefully mapped where they looked and what they found, and they concluded that when you correct for bias, the clustering is less significant, maybe even within the range of normal variation. But Batajan and Brown fought back. They reanalyzed the OSOS data and showed that even with bias corrections, the clustering is still statistically significant. The debate is ongoing. It's messy. It's complicated. But the fact remains, no alternative hypothesis explains the data as elegantly as Planet 9. There's also the self-gravitating disk hypothesis. Instead of one big planet, maybe there's a ring of smaller objects, a dense belt of Pluto-sized worlds that collectively have the mass of several Earths. Their combined gravity could, in theory, create the clustering we see. But this hypothesis has problems. For a disk to stay stable over billions of years, it needs to be very specific in mass and distribution. Too much mass and it collapses into planets. Too little and it disperses. The Goldilocks zone is narrow, and there's no evidence we've ever seen of such a structure anywhere else in the universe. Vera Rubin will test this too. If there's a hidden belt of large objects, the survey will find them. Within a few years, we'll have a complete census of everything larger than 100 kilometers in the outer solar system. If the disk exists, we'll see it. If it doesn't, Planet 9 remains the best explanation. And if Planet 9 doesn't exist at all, if the data is wrong, or the bias is worse than we thought, then we're back to square one. We're back to a solar system that makes no sense, where Sedna is impossible, where the orbits are random, where the universe is messier and less predictable than we want it to be. Personally, I don't think the data is wrong. I think something is out there, and I think we're about to find it. Because the Vera Rubin Observatory is not just another telescope, it's the telescope. It's the machine we built specifically to find hidden things, fast-moving asteroids, distant supernova, dark energy, and yes, Planet 9. If it's a planet, we'll see the reflected light. If it's a black hole, we'll see the lensing events or the accretion flares. Either way, the silence ends, the decade-long mystery resolves, and we'll finally know what's been pulling at the edge of our solar system for 4 billion years. The data is streaming in right now. Every clear night, Vera Rubin opens its 3 gigapixel eye and watches the sky. The astronomers are processing the images, running the detection algorithms, looking for anything that moves, blinks or lenses, and somewhere in that data there might already be a signal, a faint dot moving against the stars, or a star that briefly brightened and dimmed in a way that suggests a tiny, dense object passed in front of it. We might already have the answer, we just don't know it yet. Because analysing this much data takes time. The legacy survey of space and time will run for 10 years, but the first major results will start coming out in the next few months. Papers will be published, press conferences will be held, and if they find it, the world will know. The discovery of Planet 9 would be the astronomical event of the century. It would be front-page news. The first new planet discovered in our solar system since Neptune in 1846. A super-Earth in the outer darkness. A hidden world that's been there all along, invisible, waiting. Or, the discovery of a primordial black hole would be even bigger. It would confirm a theoretical prediction from the earliest moments of the Big Bang. It would prove that black holes don't just come from dying stars. It would give us a local laboratory to study quantum gravity, Hawking radiation, and the event horizon. It would rewrite textbooks. It would win Nobel Prizes. It would change everything. So the stakes are high, the search is active, the data is coming in, and the answer is close. But until we have that answer, the mystery remains. Something is out there. We can feel its gravity, we can see its effects. We just can't see it. Not yet. And that invisible presence, that silent shepherd in the darkness, is either a frozen super-Earth drifting through the void, or a grapefruit-sized puncture in space-time left over from the birth of the universe. Either way, it's ours. It belongs to our solar system. It's been with us for 4 billion years. And it's time we said hello. The Vera Rubin Observatory is watching. The data is accumulating. And in the next 12 months, the ninth sibling will finally reveal itself. Whether it's a world or a singularity, we're about to find out. I'll be here when the announcement comes, covering the data, breaking down the implications. Because this is the kind of discovery that changes how we see our place in the universe. This is the kind of mystery that reminds us how much we still don't know. And this is the kind of story that doesn't end until we have proof. Subscribe. Because when Planet 9 is found, or when the first microlensing event is detected, you'll want to be here. This is the year the darkness speaks, and we're finally ready to listen.